Hello friends, welcome again to this channel, and in this session we will discuss Poisson distribution and its applications in traffic engineering. Now let us first understand what is Poisson distribution. It is a discrete function which is used to model the number of events occurring within a given time interval. It is used to model random phenomena, particularly when number of failures of an event to occur are impertinent, like number of accidents on a highway. Now we know how many accidents have occurred on a particular section of the highway, but we do not know, or we do not want to know, what are the accidents which did not occur. Similarly, number of arrivals on a reference line. Now we can count the number of arrivals which have arrived at the reference line, but we do not know how many vehicles did not arrive, how many vehicles terminated their journey before the reference line, or how many vehicles made a right turn or left turn at intersection before the reference line. So when these failures are not important, then this model can be used to predict the probability of certain event happening when we know how often the event has occurred. Means if you know the average rate of occurring, then you can find the probability of certain event to happen. And it is also used to make forecast of a random event, either accidents on a spot or the availability of parking lot in an area or something like that. So let us see how this Poisson distribution is derived. It utilizes the famous mathematical constant E, which is also called Neperian constant, and you might be knowing that E is given by this series, summation of infinite number of infinite steps of this series. Now if you write this equation with the e to the power m, then this becomes like this: 1 plus m square upon factorial 2 plus m cube of factorial 3 and so on. Now this is the exact term in this series, and if this has to be a probability distribution, then sum of all these terms must be equal to 1. So to get this equal to 1, we divide this both sides of this equation by e to the power m. So it becomes like this: 1 is equal to e to the power minus m multiplied by the same series. Now in this equation, this is the general term, m to the power x divided by factorial x into e to the power minus m. That becomes a general term, and here m is the mean of the distribution. So this m is also called the shape factor, and the function, the probability function of Poisson distribution is very skewed for low value of m. For example, for m is equal to 1, you have majority of the value towards 0, and as m increases, it tries to shift towards the right, and it becomes symmetrical also. So if you see the application of Poisson distribution, applications are in the analysis of arrival rate at a given point on a highway. It can be used to determine the probability of finding a vacant parking space. It can also be used to study the accidents on intersection or on highway, or it can also be used to design the turning pockets at intersection. And there can be several other applications which you can find either in transportation engineering or in traffic engineering. Any random event can be modeled using this distribution. The limitations of Poisson distribution are that it is appropriate for describing random events only. And the first condition is that the mean should be close to variance. It need not be exactly equal, but it should be very close to equal. Mean should be equal to variance, and it is only applicable for discrete events. So the value should be 0, 1, 2, 3, 4, 5. It cannot be 1.2, 1.3 as in the case of continuous probability distribution. So when you say random event, so it is only applicable in light traffic conditions where there is no external factor which can influence the traffic stream, like signals. It is not suitable when traffic becomes congested or when there is a disturbance due to signals in the traffic stream, or when mean and variance are significantly different. These are the properties of Poisson distribution. It is defined by a single parameter mean, which is generally noted by m. In some textbook, it is lambda also or mu also. The distribution function is the probability of x is e to the power minus m into m to the power x upon factorial x. It can also be used in Excel sheet with the function Poisson x m0, x value 0, 1, 2, 3, 4. M is the mean and 0, we put 0 here. If you want mass function, we put 1 if you want cumulative probability. Range of this distribution varies from 0 to infinity. The mean and variance are same, and m is also called the shape factor, which indicates the average number of events in the given time interval. It is also important to note that shape of a Poisson distribution will change with m, and as I already shown that when m is 0, m is low value, then it is highly skewed towards 0. Now, Poisson distribution can also be derived as a special case of binomial distribution. If you remember, in binomial distribution, I told you that P is the probability of success and Q is the probability of failure. There are only two events that can occur, either failure or success, and NP is the mean. Now, if N is very large, then P will be very small. The probability of success will be very small, and this mean NP will be just moderate. Now, binomial distribution is written like this: that P, the probability of x is equal to x, NCx, p to the power x into q power n minus x. Now, if you take NP, that is the mean, equal to m, then in this equation, P can be written as m upon n. Then this equation becomes like this. NCx, if you expand it, it will be n into n minus 1 into n minus 2 and so on, n minus x plus 1 divided by factorial x. Now, this is the product of x terms, and this remains m upon n power x, and it becomes q becomes 1 minus p, and therefore it is 1 minus m upon n to the power n minus x. Now, this, if you take this n outside this bracket, so it will be n power x. So this can be divided into x terms here. So it will be like this, that n upon n into n minus 1 minus upon n, n minus 2 upon n, and so on, m to the power x divided by factorial x into this term into this term. So this will converge to 1. Each term here will converge to 1 as n tends to be infinity. N upon n naturally 1. This can be written as 1 minus 1 upon n, so it will be 1. This can also be written as 1 minus 2 by n. It will also be 1, and so on. This term is e to the power minus m. And this term will also reduce to 1 when n is infinite. So this equation can be, when n tends to be infinite, this is 1, this is 1, this is 1, 1 is to 1 is to 1 is to x times, and then n to the power x upon factorial x into e to the power minus m into 1. So this becomes the probability distribution function e to the power minus m into m to the power x upon factorial x. X varies from 1 to 3. X can have any value 0, 1, 2, 3, 4 and so on. Now this is the Poisson distribution. So that is how binomial distribution can be reduced to Poisson distribution if the sample size is very large. Now let us take one example to explain the application of Poisson distribution. The example is that number of vehicles arriving per second interval in an intersection approach is given in the following table. For each 10-second period, there is the arrival. When there is no arrival, this frequency is 94. When there is one arrival in 10 seconds, there are 63 such occasions, and 2, 3, and more than 3, and so on. So the question is whether this arrival follows the Poisson distribution or not. So what we will do, let us calculate first the mean rate of arrival. So if you make this table here, the arrival 0, 1, 2, 3 and more than 3. See, observed frequency is 94, 63, 21, 2 and the total vehicles arriving in each time period. Because there is no vehicle arriving in this time period, so 94 into 0, there will be no vehicle in 94 times. In 63 frequency or in 63 occasions, there were only one vehicle, so total number is 63. In 21 occasions, there were two vehicles, so 21 into 2 is 42, and so on. This total is coming 111. But the total frequency is 180. That means 180 is the data set. 180 into 10 second, that is 1800 second is the time when this experiment was conducted. Now you can calculate what is the mean rate of arrival. Mean rate of arrival would be total vehicles, that is 111, divided by total periods, that is 180, and that gives you 0.617. 0.167 vehicles will be arriving on an average in a time interval of 10 seconds. So this is the value of m. Now using this value of m, if you write equation for probability, it is e to the power minus 0.617 into 0.67 into x and divided by factorial x. So if you take value of x 0, 1, 2, 3, you can calculate the probability of x. This can be done through Excel sheet also. Open an Excel sheet and here you find the function fx, press it. It will take you to a window where you can find Poisson distribution. Click OK. Another window will pop up and here you will enter value of x 0, the mean 0.617 and cumulative, we do not want cumulative and therefore it will be 0 here. So it will give you directly value 0.539. Now this, if you press OK, it will be entered into the cell. Similarly, you can find probability value for x is equal to 1, 2, 3 also. So enter these probabilities here in this column. You have 0.539, 0.333 and corresponding to each probability, if you multiply by 180, that is the total periods, then you will get the theoretical frequency. 180 multiplied by 0.39 gives you 97. 0.333 multiplied by 180 gives you 59.9 and so on. Now, if you compare these theoretical frequencies with observed frequency, you will find that there is a good match. 94 against 97, 63 against 60, 21 against almost 19, and 2 against 4. So we can say that the arrival follows the Poisson distribution. There are statistical tests to know exactly the arrival pattern follows Poisson distribution or not. We can conduct chi-square test and details of the chi-square test I will give you in a separate session. Now let us take one more example. And the statement is that intersection approach has right turning volume of 90 vehicles per hour. The traffic is controlled by an actuated signal with an average cycle length of 100 seconds. What is the probability of skipping the green phase for right turn traffic? means there will be no arrival of right turn in a particular phase. And how many will be skipped in 1 hour? Now, if it is a simple problem, the number of cycles in 1 hour will be 3600, that is the number of seconds, divided by cycle length, that is 100. So there will be 36 cycles in 1 hour. Now, average number of right turning which are arriving at the intersection in a cycle is 90 vehicles per hour. And in 1 hour, there are 36 cycles. So in one cycle, there will be 2.5 vehicles arrivals. So that is the mean rate of arrival. So if you put value of m equal to 2.5 and you find the probability that there will be no arrival in a particular cycle, x is equal to 0, then this value is 0.082. That means there are 8.2% chance that a right turning vehicle will not arrive in a cycle and the green phase will be skipped. So if there are 36 cycles in 1 hour, how many cycles will have no right turn? So 36 multiplied by this probability, it gives you 2.9, or you can say 3 cycles per hour. So friends, what we have learned in this session is what is Poisson distribution, what are its limitations and conditions, and how it can be derived as approximation to the binomial distribution. And we have explained the applications in traffic engineering with the help of 2 examples. You can write your observations and questions in the comment box, and see you again in the next session. Thank you.